Hello everyone, and welcome back to our second lesson in dynamics. If you recall, last time we talked about Newton's first law, so it is only natural that right now we'll dive into Newton's second law and try to understand the statement. The goals for this video are quite straightforward. After this lesson, we should be able to state Newton's second law and understand its implications, calculate the net force acting on a given system, and apply Newton's second law in any problems that may appear. In the world of introductory physics, Newton's second law is one of the most important laws you learn. It's used in almost every chapter of every physics book, and so it's important to master this law as soon as possible. We know objects can only accelerate if there are forces on the object. Newton's second law tells us exactly how much an object will accelerate for a given net force. In other words, Newton's second law states that the acceleration of an object is directly related to the net force and inversely related to its mass. In other words, if the net force were 3 times as big, the acceleration of the object would be 3 times as large. Similarly, if the mass of the object were doubled, the acceleration would be half as large. Now, we need to focus on a small discussion because when stating Newton's second law in the previous slide, we assume the system or the body has a constant mass. However, that is not always the truth. While it is not natural to think of examples when a system mass varies, they do appear in real-life situations. A cart that releases sand along the way, a rocket that uses its fuel to propel, or a boat in the moment of unloading cargo are all examples of such systems, for which Newton's second law doesn't have the same form. Why? Because we don't know what mass to consider. In those cases, we say that the net force gives the change in momentum of the system or of the body. And this fixes the problem because momentum is defined as mass times velocity, and therefore change in momentum will include both a change in velocity, which gives the acceleration, and the change in mass that now will appear. Now, from this Newton's second law, we can write an expression for acceleration. Relating acceleration to force, this expression will be very important as it creates a connection between kinematic quantities and dynamics. We said the equation that arises from the law statement is simple in fractional form. Acceleration is force divided by the mass of the object on which the force acts. Since force is a vector, we can rewrite Newton's second law by adding a vector sign to both force and acceleration. This shows that the direction of the total acceleration vector points the same direction as the net force vector, which we intuitively see is correct. We know from practice that if the net force F points right, the acceleration A must point right as well. If the net force points to the left, the acceleration will also point left. Now, um, did you notice that in the statement we named net force and not just any simple force? That is because um, the net force gives the total force acting on the system, and therefore this is the one that gives the total acceleration. Recall from previous lessons that the net force acting on a body is the vectorial sum of all forces acting on the given body. We can find this net force at least on the drawing on the right hand side just by the triangle rule or the parallelogram rule and vectorially adding forces 2 by 2 to find that one force that would have had the same effect as all other forces combined. Now, let's look at some examples to understand how to apply Newton's second law in problems that we may encounter, and in particular focusing on how to compute the net forces in two familiar cases, addition and decomposition. In our examples, there are only two forces acting on a given body, but the same idea can be used for any number of forces in any context. For addition, sometimes, especially when the body's motion is linear, meaning that the body moves in a straight line, it is useful to add all the forces to obtain the net one, which will be in the direction of that straight line. As we remember, a force is a vector, so we must vectorially add the distinct forces. Look at the picture. The two forces acting on a body at rest have, let's say, a 120 degrees angle between their directions. Using the known formula, we can find the magnitude of the net force, which would be precisely square root of 19. And using the graphical method of the parallelogram rule, we can find the direction of the net force just by creating a parallelogram with sides at the length of and direction of the vectors and uniting the net force on the diagonal. And this way you can find the direction of the net force and hence the direction of the new motion. To find the magnitude, we use the known formula that is taking the square root of a more complicated expression, that is the sum of the two forces squared plus a mixed term that is 2f1, f2 cosine of the angle between the two vectors. And we are lucky now because cosine of 120 is minus 1 over 2. So we just replace that. We obtain the expression on the last line and then just plugging in, for example, 5 newtons and 3 newtons, we obtain our force, or you can just plug in any other values. Having, having found both the magnitude and the direction, we found the net force, and then giving the body a mass of, let's say, 2 kilograms, we find the cosine acceleration just by dividing this force by 2. Now we can go into the second case because it's not always as simple as in the first one. Recall that motions on perpendicular or orthogonal directions are independent. We can use that fact to decompose some forces when the motion directions might change as the direction of orthogonal axis is fixed. This way, we find the acceleration corresponding to each perpendicular axis, which will still give a comprehensive characterization of the motion. Look at the picture for our problem. Along with the body and the two forces that we can see, I drew an orthogonal system of coordinates with the OY axis pointing upwards, the OX axis pointing to the right, and the OZ axis pointing towards the reader. As you can see, the first force of magnitude 5 newtons is along the OY direction. However, the second force of magnitude 10 square root of 2 newtons is not along any of the axes. It makes a 45 degrees angle with both axes in the plane. We'll decompose this in two components, one along each axis, using the known trigonometric formula. And then we find components just by multiplying by sine of 45 degrees and cosine, and we obtain, in this case, luckily, two components of the same magnitude, F2 along x-axis, 10 newtons, and F2 along y-axis, also 10 newtons. Recall that the use of sine or cosine is very prevalent in physics problems, especially in mechanics. So remember the definitions. Now that we already have forces along the axis we considered, it is easy to compute the respective net forces and find the corresponding acceleration for a mass of, let's say, 5 kilograms. For the y direction, we see that we have two forces, that would be the whole F1 and the y component of F2. And since they are parallel, we can just add them as we would add any quantities algebraically and obtain 15 newtons. Then just dividing by 5, we find the acceleration of the body along the y-axis would be 3 meters per second squared. Now, along the OX-axis, things are a little bit simpler because we only have the component of F2, which we already know was 10 newtons, which will then give an acceleration of 2 meters per second squared along the x-axis. We finish with this lesson, and the main takeaways from this video would be that Newton's second law states that the acceleration of a body is directly proportional to the force that prompted and inversely proportional to the body's mass, that the net force, which we understand to be the total force acting on a body, is the vectorial sum of all forces acting on that body, that in problems it is useful to compute the net force through addition or decomposition. Thank you for your attention, and I will see you next time in our next video, where we will talk about Newton's third and last law and finish our journey to dynamics. Goodbye.